Okay, now let's move on to part C, and I need a page for that. Bloop, bloop. Okay, so for part C, we've got these bullets in the tank, and each bullet's change of momentum is we found the last time. So what I'm going to say here is the impulse that the tank exerts on the bullet, is that change in the bullet's momentum, right? So that's the negative 50.8 I hat plus 25.1 j hat kilograms times meters per second. Okay, so each bullet that comes along, the tank exerts this much impulse on it. What that means is that the bullet also exerts the same impulse in the opposite direction back on the tank. So the impulse the bullet exerts in the tank is going to be equal to the negative of what I just wrote, of the impulse the tank exerts on the bullet. So this line here is saying impulse bullet exerts on tank is equal to the negative of impulse tank exerts on bullet. So, with that said, now the next step of the way is to say, okay, well, we've got these bullets coming along. There's 250 bullets per second hitting the tank. Each one provides this impulse. What's the average force? And so what you can do is you can take some stretch of time and take the total impulse over that time, divide by the change in time, and find the average force. So let me show you. Here's a force versus time plot. A bullet hits a tank like boom, okay? And then 1/250th of a second later, a bullet hits another bullet hits the tank, sorry, and another bullet, and another bullet, and another bullet. And these all go at the rate of, 250 bullets per second. So what we just calculated is essentially the area of one of these humps. Now I'm using area loosely because this is a vector quantity, this impulse. So it's not exactly we're somewhat comparing apples and oranges here, but not really, because we just have to imagine there's a force in the x direction, a force in the y direction, and the area under the fx curve would be this x impulse, and the area under the fy curve would be this y impulse. Okay, so we want to take the stretch over some span of time delta t. We can then add up the total area under these curves in that delta t time and divide by delta t. So the average force equals impulse divided by the time you're looking at. That's an I and that's a delta t. Sorry, my horrible writing. So where this takes us then is if we look at, say, 1 second, we can say, okay, in 1 second we get 250 bullets. Okay, so we have 250 of these little humps. 1, 2, 3, 4, and so on through 250 of them in a 1 second time span. So what that really amounts to is if we apply that here, we're saying the force is equal to the rate of bullets per time. So that's going to be 250 bullets per second, okay, times the impulse you get per bullet. So that's negative 50.8 I hat plus 25.1 j hat. And the impulse per bullet is kilogram meters per second. But we're getting that many we're getting that impulse per bullet. So when you do that, then you can see that bullets and bullets cancel out. The seconds and seconds become seconds squared, and you multiply it all out, you get kilograms meters per second squared as your units, which means your units are newtons for force, which is what you want. So that's fantastic. So the net force in the tank from the bullets, when you calculate it all out, is going to be, I hope, 12.7 I hat minus 6.3 j hat, and that's in kilonewtons. Now, let's see, the error I made up here just a second ago was that I plugged in this impulse the tank exerts on the bullet here, when I really should be plugging in the impulse the bullet exerts on the tank. So that should be a plus, and that should be a minus. I'm sure that's completely readable, no problem, right? Okay, so that's your answer to part C, and then for part D, you want to find the power that the tank has to exert to keep up or to keep going under the stream of bullets, and that's very simple. That's just P equals F dot V. Okay, so the tank is going to the left, which means that the velocity of the tank is negative 0.5 I hat meters per second. Okay, and so you do this multiplication, and what you get is the dot product of F and V here, and what you get is that the power required is going to be, whoops, damn it, 6,340 watts is what I get, or 6.34 kilowatts, I guess. Anyway, that's that problem. Hope that made sense. Let me know if it doesn't, and let me know how well this audio worked. I'm trying to find a good solution to, to all my problems here.